I am Yuma ADACHI from Okayama University of Science. I would like to make presentation entitled Proposal of 18-leg mobile robot seat simulator using tetrahedral-shaped flexible pneumatic actuators. This is the outline. First of all, I will show you the background and purpose of our study. Secondly, I will show you the previous mobile robot. Thirdly, I will explain the 18-leg mobile robot. Fourthly, I will show you driving test of the robot. And finally, I will give you our conclusions. According to Japanese law, occupational therapists and physical therapists can perform rehabilitation to the patient for just 30 minutes per day. Some of them recommend patients to execute voluntary rehabilitation at home. According to a medical report, voluntary rehabilitation might prevent bedridden state, various disease, and disease syndrome. In the previous study, we developed the quadrant device using the six-legged mobile robot as an amusement element. In this study, we aim to develop an 18-legged mobile robot with improved load capacity that can be used in actual use. This is the image of for training device. For example, a user is sitting on a cushion-type device while playing virtual games using VR goggles. The device can give radial inclined angle, rotation, and translation motions and vibration to assist with user. Therefore, we developed a low-height mobile robot using six legs that can rotate and translate toward radial direction. Next, I will show you the actuator for legs in the robot. As an actuator of the robot legs, we use an extension type flexible pneumatic actuator like this figure. We call it EFPA for short. The actuator consists of a silicon rubber tube covered with a bellow-type nylon sleeve and two acrylic end connectors is the supply port. The operating principle of EFPA is as follows. When supplied pressure is applied to the actuator, the rubber tube extends toward radial and longitudinal directions. As the sleeve can only deform toward longitudinal direction, the actuator extends longitudinally. The actuator can extend more than about 2.5 times of the original ranges when pressure of 400 kPa is applied. The maximum on cooling force is about 60 Newton. Next, I will show you the previous six-leg mobile robot and the tetrahedral-shaped pneumatic actuator used as a leg in the previous robot. The bottom video shows translation motion and the upper video shows rotational motion using the previous robot. The previous robot can translate in six directions and rotate both clockwise and counterclockwise. In my research, I aim to improve the rigidity of these legs by making them smaller and to improve their load capacity by increase their arrangement density. The previous TSA had a program on buckling during pressurization based on its flexibility. Therefore, we reduced the size of the TSA to increase its rigidity. In addition, to increase lifting force, the setting angle of EFPA is also changed to 75.6 degrees from 60 degrees. As a result, the maximum generated lifting force increased to 150 Newton compared with the previous one of 130 Newton. That is about 1.2 times. Next, I will show you the small size six-leg mobile robot using small TSAs. The bottom video shows translation motion and the upper video shows rotational motion using the small size robot. The lifting force become larger even if the frame size of become one third. Next, I will show you the 18-leg mobile robot using miniaturized TSAs with consideration of actual use. This figure shows the upper and side view of the robot. The yellow circle indicated the frame size of the small size six-leg robot. This figure shows the arrangement of 18 legs in the robot. The black circle indicates EPS and black triangle indicate TSS. In the robot, 12 legs are added radially to the previous small size 6-leg mobile robot. By making each of 3 legs surrounded blue triangle performs the same action. The same gate of the previous 6-leg robot can be used. Next, I will show you the comparison of brain size and maximum lifting force of the previous and improved mobile robot. The brain size of the 18-leg robot is about 1.4 times that of the previous 6-leg mobile robot. But as the number of legs increases, the estimated maximum lifting force is 2,700 Newton. That is 3.2 times that of the previous 6-leg mobile robot. 18-leg robot can generate sufficient force against vibration even when a person rides on it. This figure shows the classification of EFPS operated by same valve in the grouped leg. By repeating the same colored EFPS with the same valve, the improved robot can be operated by same number of valves as the previous 6-leg mobile robot. In addition, we use a little large size valves compared with the previous valve in the previous small size 6-leg robot. This figure shows the schematic diagram of control system of the improved robot. The system consists of an embedded controller with a Bluetooth communication unit, taking on-off valves, and the improved robot. We can operate the robot wirelessly by selecting a sequential program to drive valves according to the translated character code from the tablet via Bluetooth. The robot can be operated by using the Android tablet with a Bluetooth serial controller. Next, I will show you the result of the translational motion using the previous robot. The left table shows the time chart of sequential driving pattern for each EFPA for translational motion. The right figure shows the transient response of acceleration for X, Y, and Z axis of the previous robot during translational motion. The translational motion is as follows. While lifting the full robot by extending 3 TSS, other TSS bent towards the propulsion direction as a free leg. After that, while making the robot body down by contracting the extended TSS, the other TSS are bending towards the opposite direction. Although this gate can perform translation while ensuring stability, we find that the Z-axis acceleration is relatively large. It means that it isn't as comfortable as a simulator. The right video shows the proposed translation gate. The gate is a simplified version of the previous gate. The left table shows the time chart of sequential driving pattern of each EFPA. First, 9 legs indicated by the red triangle in the right figure bent towards the opposite direction against moving. As the robot is lifted by other legs while 9 legs retaining the bending state, the robot can move. Next, I will show you the transient response of acceleration in the Z-axis and Y-axis directions for the translational motion using the previous and the improved robot. The left and right figure shows results of Z and Y-axis acceleration respectively. The red and blue line show the result using the previous and improved robots respectively. Compared with the previous one, the improved robot with proposed gate can give almost same acceleration in the y-axis direction. However, the z-axis acceleration of the improved robot can be significantly reduced. Therefore, you can see that improved robot can give more sightable as a seat simulator. In addition, also the translational motion of the previous robot is affected by the friction with the floor. We can confirm that improved robot can achieve the same translational motion even on circular floors or floors with high friction. The right figure shows the relation between moving displacement and speed of the robot when the switching time t on the left time chart is changed. The orange line indicates the moving distance for one cycle. The blue line shows the moving speed. We can see that the maximum moving speed of 13.7 millimeter per second and distance of 26 millimeter can be also obtained at the switching time. T is 1000 milliseconds. Next, we will show you the operation using improved translational gauge 2 compared with the previous gauge. After lifting the robot by other legs, 9 legs bent towards the propulsion direction. After that, they bent towards the opposite direction. While lifting by other legs, by this method, the moving distance becomes larger than the previous one. The left figure shows the relationship between moving displacement and speed in the switching time t for legs bending opposite as shown in the left frame on the left table. We can see that the bending motion was saturated from the switching time t is 1150 milliseconds, and the maximum moving distance of 50.3 milliseconds and the maximum speed of 15 millimeter per second can be obtained at switching time of 1150 milliseconds. I will show you the continuous rotational motion of the robot. In this movement, the driving pattern covered by the red frame on the left time chart is repeated. By adjusting the number of repetitions of this pattern, we can decide moving this pattern. This video shows the continuous rotational motion, similar to translational motion. The rotational motion is realized by repeating the driving pattern covered by red frame on the left time chart. Covered with using rigid legs, it is not necessary to adjust bending angle between inner and outer legs in the robot by using flexible legs because bending angle of legs are adjusted automatically because of its flexibility. Therefore, smooth rotational motion can be realized. This study can be summarized as follows. We propose and prototype 18-leg mobile robot using miniaturized CSS to increase the load capacity. We confirmed that the tested robot could be realized continuous translational motion and continuous rotational motions. As a future work, we are going to investigate optimal acceleration while the patient rides on the robot as a sit simulator.